Welcome to another podcast. This episode we're going to be taking a look at an important series known as the Binomial series. The Binomial series is one of the more important series in all mathematics, particularly because it can describe a variety of situations where we're raising things to powers. And the binomial comes from the fact that you're raising two things which are added to a power. The basic idea here is, think about something like this. What is the expansion look like for x plus 3 squared? Well, it's x squared plus, remember what you do, you multiply this by 2, so it would be plus 6x plus 9. The binomial series can tell us how to get the 6 and how to get the 9 and also how to get the 1. So the binomial series is sort of a more generic version of squaring terms or cubing terms or whatever you may have for these binomials. So this thing is called a binomial. And so the binomial series is an incredibly important series where it gives you the expansion for an arbitrary power. So what if I wanted to know what x plus 3 is to the k instead of just x plus 3 squared? So the function that I'm looking at is the function 1 plus x to the k for arbitrary k, and we're going to assume here that k is real. So this is for any real constant k. This also includes negative values of k, fractional values of k, so it's not just integer values, it can be any value of k. So if k was 1/2, I'd be looking at the square root of 1 plus x. So if I want to recover its Maclaurin series, which is what I want to do here, then I need to calculate some derivatives. And values of the function is 0. So I'm going to start with f of x is 1 plus x to the k, which means that f of 0 is 1 to the k, or just 1. For any value of k, 1 to any power is going to be 1. So the derivative of this is k times 1 plus x to the k minus 1. And therefore the derivative evaluated at 0 is k times any power. You get 1 raised to a power again, so it's just k. F double prime is k times k minus 1, 1 plus x to the k minus 2. And if you evaluate that at 0, you get this k times k minus 1. And I think you can start to see the pattern come out here. If you take the nth derivative of x, then what you end up with is k times k minus 1 all the way down to k minus n plus 1. So you can look here, that's what happens here. It's the second derivative, and you end up with minus 1 because it's minus 2 plus 1. So this is the derivative, would be 1 plus x, then would be to the k minus n. And so if I evaluate that at 0, evaluated this at 0, it would just be k times, you get all these terms that keep coming down, right? These are the powers that keep coming down in front. You'd get all these powers that have come down in front, all n of them so far. You'd get those, and you would just have 1 to the k minus n, which would just be 1. So basically, the coefficient looks like this, and I want to clean that up a little bit. So we've got that the nth derivative evaluated at 0 over n factorial, because that's what our coefficients are, right? If we're going to do the Maclaurin series, this is what the Maclaurin series coefficients look like. According to what we just did, would be k times k minus 1 all the way down to k minus n plus 1 over n factorial. However, I want to do a little bit here extra. What would be the next term? So the next term in the sequence here would be times k minus n, right? Because you'd subtract 1, so k minus n would be the next term. And if I went k minus n all the way down to 1, then that would extend the fraction, and the piece that I added here, this k minus n all the way down to 1, is just k minus n factorial. So I can't change the problem, which means that if I added it to the numerator, I also have to add it to the denominator. So I multiplied the top by k minus n factorial, and I multiplied the bottom by k minus n factorial. Well, the reason I did this is because now if you look at the numerator, we start with the value k, and we go all the way down to 1. This means that the numerator is k factorial over n factorial k minus n factorial. That is what the coefficients for the binomial series look like. It turns out that these have a very special notation attached to them in mathematics, and it's something called the binomial coefficient, obviously because it's the binomial series, but what I'm talking about is the notation for this as k choose n, and that's how you should read this. You should read it as k choose n, because as we'll see here in a second, this is counting the number of ways that you can get the x values to line up when you FOIL things, and I'll talk about that here in a second. But kind of taking this one step further then, if our function is 1 plus x to the k, then we've just figured out that its power series representation, in fact its Maclaurin series representation, is given to us by the sum n goes from 0 to infinity of k choose n x to the n, which is the same as, going back to the original formula that we had right here, it's the same as k times k minus 1 all the way down to k minus n plus 1 over n factorial x to the n. So this is the main thing you need to take away, is these two forms of the sum for what's called the binomial series. Now I want to add a little bit more to that. In particular, I want to look at the factored out form. So 1 plus x to the k, if I start to compute these values, so I'm going off of this format right here, then when n is 0, you just get k and then k here, so that's just k in the top, over 0 factorial. So what you end up with here is when n is 0, you get 1, and when n is 1, you get kx. When n is 2, you get k times k minus 2, or k minus 1, excuse me, over 2 factorial x squared. When n is 3, you get, when n is 3, so the third term here, you get the following, and this just keeps going. What I want you to realize here is the easy way to remember how to do this is you start with the k power, or you start with the k term, and then if it's a squared, you've got two terms. So here's the first power to come down, here's the second power to come down. If it's x cubed, you've got k, then k minus 1, then k minus 2, and so you've got 3 of these here. In other words, the number of factors matches the power, matches the factorial. All of those match. And so if I asked what is the 20th term of the binomial series, you could tell me easily that the coefficient there is k times k minus 1 times k minus 2 all the way down to, well, there's got to be 20 of these, right? So if there's got to be 20 of these, then that would be all the way down to k minus 19. And then this would be over 20 factorial x to the 20. So this is the 20th term of the power series for the binomial series. And the idea is that there are 20 of these factors. And so that just gives us a quick glimpse at what the binomial series is. I do want to add that the binomial series has a strict radius of convergence. The radius of convergence of this is 1, which means that the binomial series converges as long as the absolute value of x stays less than 1. So that's an important thing to remember here, is I can only plug values into this series that are between 1 and -1. We're going to have some follow-up videos to this where I show you how to calculate some binomial series using these formulas, but I wanted to introduce you to what is considered to be one of the most important series that we have access to. And we're going to do some follow-up with this in some future videos. All right, thank you for watching.